Welcome to lecture number 9 of modern construction materials. Today we are going to talk about fracture mechanics, and fracture mechanics is important because lot of materials fail in a brittle manner, and when defects occur in them, then things get worse. These defects propagate into cracks and you have sudden catastrophic failure. I start with this picture of the Meenakshi Sundareswari temple in Madurai, which is about 600 to 800 years old, and most of it is made out of granite, and around this temple tank we have many columns of stone. Some of these stone columns have started to crack and they are being replaced, and this cracking is due to settlement of the ground around the pond and many other environmental factors. What else can fracture cause? Brittle fracture can cause sudden failure, as we see in this picture, where cracks occurred in the fuselage of this plane while it was in flight, and part of the fuselage just came off. Most of the people surprisingly survived because they had their seat belts on. What happened was, in this Boeing 737-297 that was flying in Hawaii, was that a crack propagated along the section that was riveted. After many flights, due to fatigue loading, defects had started to propagate along the circumference of the fuselage where it was riveted. A crack suddenly developed and the fuselage was torn away. Unfortunately, some people were killed during this accident. Another case that we have already discussed is that of the failure of the Liberty ships and some T2 tankers that were built in World War II, and a similar behavior also happened in the Titanic, or what they say happened to the Titanic when it sunk. Here the weld that was used, due to the cold weather and fatigue, became brittle and a crack propagated. This is what was seen in one of these ships in the Boston harbor. Crack developed and suddenly this ship broke into two. Brittle fracture can occur in smaller levels, smaller scales, but with disastrous consequences, like in this case of a pipeline failing in Australia, which led to the spilling of about 2 million liters of crude oil, causing ecosystem damage in the mangrove lined canal flowing into the Brisbane river in 2003, huge financial loss and huge ecological loss. Another very interesting case of a catastrophic failure occurred in two of the three steel girders of the Huan Bridge in Milwaukee in the US in the year 2000, and here a generally ductile material such as steel, due to the triaxial constraint that was brought about by the bracing system, led to brittle crack propagation instead of a ductile failure. It was confined so much, it was constrained so much that the material could not yield, but failed due to brittle cracking. And these are some of the cracks that you see in the flange and in the web plate. This occurred over a period of a few hours and the bridge was then made unserviceable. More brittle materials are more prone to fracture. These are pictures of the Wuxi Bridge during the Chi-Chi earthquake in Taiwan in 1999, where there was a fault very near the bridge and the bridge had a lot of lateral loads, resulting in severe cracking of the piers, large movements about 2 meters that the bridge was not designed for, and the concrete, though it was reinforced, failed by cracking. So, why fracture mechanics? What is different about fracture mechanics? Conventional design procedures that are based on the maximum stress criterion are not always adequate. Failure theories and concepts that we discussed in the previous 2 lectures, always consider a material free of defects and free of discontinuities. Fracture mechanics now determines failure based not only on the applied stress, but also on the crack or the flaw that is present, and brings in new materials parameters like fracture toughness instead of just the stress or the strain limit. Instead of the magnitude of stress or strain, which are very difficult to determine, have very high values in any case near the crack tip, fracture mechanics is concerned primarily with the distribution of stresses, the stress fields and the displacement fields in the vicinity of the crack tip. This is particularly applicable to brittle materials like concrete, rock, glass, ceramics and so on, but under certain circumstances other materials also fail in a brittle manner, like we saw in some of the examples of the pipes and the girders. Fracture mechanics also helps us understand why there is such a large difference between the theoretical material fracture strength that we can calculate from the bond energy. Remember, when we looked at the Condon-Morse diagram linking the energy with the interatomic distance, there was a bonding energy, and we could also see what happens to this bonding energy as the distance between the atoms changes. So, if we were to calculate the strength of the material from those values of bond energy, we would find that that is much higher than what is actually measured in the lab on a material, probably 2 to 3 orders of magnitude higher. So, there is a big difference between the actual strength and the theoretical strength, the actual strength being much lower than the theoretical strength. The reason for this was categorically stated by Griffith in 1920, when he concluded that any material, any real material has flaws, micro cracks or some other defects, and these defects concentrate the stress so much that the theoretical fracture stress is reached in small points, small locations, in small areas localized around these defects. So, as the theoretical fracture stress is reached at those points, the cracks start to propagate, even though the applied stress is less than the theoretical fracture stress, and finally fracture occurs. Now, let us try to visualize how stress concentration is induced, and for this we look at this simple diagram. On the left we have a panel subjected to a tensile load. So, these are the applied stresses sigma outside the panel. Now, imagine a channel with water flowing in it. Okay. So, these lines would then be the stream lines, water is flowing. Similarly, we can visualize in the case of a panel under stress that these would be the stress flow lines. So, stress has to go from one end to the other through the body. So, these are can be called the stress flow lines. Now, going back to the channel with water flowing example, think of what will happen if you put your hand at one of the edges. You put your hand into the flowing water, and what would happen? You would have now water moving faster along the edge of your hand, because you have blocked a part of the flow, and you will find some currents, eddy currents forming around the edges. So, there is a concentration of flow, there is a faster flow occurring at the edge of your hand, because you have blocked part of the channel. Now, coming back to our stress example, a similar thing happens. Suppose I have this panel and I make a cut in it. So, I decrease the section, I force the flow of stress to go around this cut that I have made or a notch that I have made. So, here you have a zone of stress concentration. So, the stress concentration occurs at here, and we find that the stress here can be actually much higher than the stress applied far away from this defect or the far field stress. This stress now can reach at a small area the theoretical fracture stress, even though the stress applied far away is much less, and this causes the propagation of the crack, makes things worse, higher stress concentration, and the failure continues. So, stress concentration can be visualized as a concentration of stress flow lines due to some geometrical discontinuity in the continuum. Now, there are lot of equations which describe the stresses that form around defects. We can look at the case of an elliptical defect or void in a plate, say an infinite plate subjected to a tensile stress sigma sub t. You have now a defect or a crack inside, and this defect is now we assume in the form of an ellipse defined by a length of 2c and a width of 2b. The radius at the end is rho. So, let us see what happens to the stresses in the vicinity of the crack tip. So, we go here, this is now the crack tip with a semi length of c, a semi length of b. This is, as I told you, the radius of the crack tip, and if we consider a case of c equals 3b, a solution given in Young, we find that the stress in this direction, in the direction of the pull caused by the applied stress, we find that at the crack tip this stress is almost 5 times the stress applied. On the x axis here we have sigma, which is the stress at any point divided by the applied stress sigma sub t. This is the sigma yy, and this is sigma xx, the stress in this direction. So, we find that sigma yy is amplified almost 5 times at the vicinity of this defect tip. Sigma xx also is quite high in here. Far away sigma xx and sigma yy will become smaller, but near the crack tip you have very high values. And what we see is that if the defect becomes sharper and sharper, that is c becomes very large compared to rho the radius, that is for a defect that is very sharp tending to be a crack, this stress now reaches infinity in the theoretical sense, that is there is a singularity of stress in the crack tip, the crack tip stresses become singular. So, this can also be understood by looking at the lattice or the atomic bonds near a crack tip. We have a far stress, that is sigma, that is applied far away from the defect or crack. Now, the stresses have to go around the crack tip like we saw in these stress flow diagrams, and it will happen that the bond which is nearest to the crack tip or forms the crack tip will be very highly stressed. Lot of stress goes through here. The stress here now is much more than sigma, and this reaches a point of failure. So, this bond breaks, and then the crack now has advanced by one lattice plane, and next the stress will be taken by this bond CD and so on. So, this crack now keeps propagating through the body. This is the reason why, even though when you have a stress that is applied which is smaller than the theoretical fracture stress, failure stress, you have failure because the bonds that are near the defect tip take very high stresses and start failing one by one. There are different ways that fracture can occur, and the 3 pure modes into which all the other modes can be put into are mode 1, where we have a tension or opening mode. This is called the opening mode, where you have a crack which is propagating due to tensile forces. So, something is opening this, we are pulling on either side and the crack opens. This is the most common mode of failure of most materials. Due to tension, the crack develops perpendicular to the applied tension and you have failure. Now, this is a shearing mode where you have a in plane shear we have a case where we are propagating a crack by shearing. This is not very common. One example is what you would have seen in a direct shear test in your soils lab, when you did a test on a rock joint or in over soil, where two sides of the material are slipped with respect to each other, which are sheared, and a crack forms here along this shear plane without much opening. So, this is called in plane shear. This has applications in earthquake engineering where there are slipping of joints. Mode 3 is called the tearing mode. This is out of plane shear. Where you have something tearing, like when you tear a piece of paper, the material now twists and you have shearing occurring out of plane. So, there is some torsion here occurring. So, these are the three principal modes. The most common is mode 1. Most of our materials that we consider are failing in mode 1 or in the tensile mode with an opening crack. Let us look more in detail in what happens in mode 1 or for an opening crack. What we can imagine is, now we have a crack, a sharp crack, and let us see what happens in front of this crack. So, the crack is advancing this way, and if we look at a stress state of a point ahead of the crack tip defined by this distance from the crack tip r and an angle theta, we would find that the stresses become infinite as it approaches, as we approach the crack tip, and this increase in stress is defined by the factor r to the power of minus 1/2. So, there is a singularity in the stresses. The stresses increase as r to the power of minus 1/2 increases. So, when r becomes 0, the stresses become infinite. That is why it is called a singular stress field, and the equations for this are given here, where we have sigma x, sigma y and tau xy, the stresses ahead of the crack tip. The point that we are discussing is defined in terms of r being the distance from the crack tip to that point, theta being the angle from the crack plane. And what we find here is, we have a term here which is K1, K1 being the stress intensity factor divided by 2 pi r to the power of 1/2, and here you see the term r to the power of minus 1/2 coming in for the stress singularity. As r becomes smaller, as we approach the crack tip, these values become larger and larger, and when r becomes 0, these stresses become infinite. The other stresses in this case would be tau x, tau y equal to 0, and sigma z, the stress perpendicular to the plane, would be mu times sigma x plus sigma y, mu being the Poisson ratio. What is important here is that we have introduced the term K1, K1 for the mode 1, which is the stress intensity factor. This is one of the terms that we will continue to give importance as we discuss fracture mechanics. K1 can be considered as a single parameter describing the stress in the displacement fields near the crack tip. To calculate it, we generally consider the material to be linear elastic and both isotropic and homogeneous, that is, the properties are uniform and the material is behaving in a linear elastic manner even though it is fracturing. This has limitations and it can be incorrect for many materials, but generally we assume that the approximations involved in the application of linear elastic fracture mechanics is reasonable. We get reasonable values and we can use these values and modify them later to bring in other non-linearities. K1 has the dimension of stress times the square root of length, such as megapascal square root of meter. How we can apply or calculate K1? Say we have a panel here with a crack of length A, and we have a far field stress applied of sigma. K1 will then be equal to sigma, which is the applied stress, times F, which is a function of the geometry, say the ratio between the width and the length, and crack length, times square root of pi A, A again being the crack length. So, through tests of this type of element we can get K1, we can find out when failure occurs, and that would be the critical value of K1. And if we know this, we can calculate K1 for any applied sigma and A. In another form, suppose you have a beam, we can put K1 in form of load, P is the applied load. Again we have a beam now with a certain depth and a certain width. B is the width of the beam, the thickness of the beam, D is the depth of the beam, and K1 could be put in the form of P divided by BD times the square root of D F alpha, alpha being the A by D ratio or the relative crack depth ratio. That is A, this is now A, and A divided by D is alpha. F alpha is a function that depends on the span depth ratio. This is now the span. The span depth ratio defines this function F alpha, and this can be calculated from numerical analysis or otherwise. So, K1 can be determined depending on the geometry of the element and the defect length or the crack length. Until now what we have discussed is called linear elastic fracture mechanics or LEFM. The main features to summarize are that the fracture criterion involves only one material parameter, which is related to the near tip stress field and the energy of the structure. The stresses near the crack tip have an r to the power of minus 1/2 singularity and become infinite at the crack tip. During fracture we assume that the entire body remains elastic, and whatever energy is dissipated during fracture occurs only at the crack tip, that is fracture occurs at a point which is the crack tip. These are the main features of linear elastic fracture mechanics, and these have limitations, they cannot be applied to all materials and all situations. In this framework, when do we consider the crack to propagate? Crack propagation according to linear elastic fracture mechanics occurs when K1 is greater than or equal to K1C. So, this is the fracture criterion. K1, if you remember, comes from the geometry of the element, the stress applied or the load applied, and the defect. K1C is a material property, it is a material parameter called the critical stress intensity factor of fracture toughness, it is a material property. So, on the right side you have a material property, and the left you have a parameter which depends on the load that you apply, the type of structure, and the defect that it has. When K1 increases and reaches a value of K1C or surpasses the value of K1C, the crack starts propagating. So, this is the failure criterion according to linear elastic fracture mechanics. We can look at a table of values of fracture toughness. We see that the values of materials that we always think of as brittle, like glass, cement, ice, rocks, other ceramics are lower, the fracture toughness is low. So, that is why these materials crack rather than yield. On the other hand, we have metals, ductile metals, the pure metals are most ductile right at the top, where the fracture toughness is so high that these materials also always yield, they do not crack or rupture. Again at the bottom we have materials like epoxies which are very brittle. Slightly higher up would be other polymers which are not so brittle like polypropylene and nylon. In the middle we have composites and wood. Wood again parallel to grain, cracks more easily, that is the grains separate. We will look at this again when we talk about timber. Perpendicular to the grain, there is a higher crack resistance, the fracture toughness is higher. Composites which are polymers reinforced with different types of fibers are more at the top. Boron fiber, glass fiber, carbon fiber, reinforced polymers. Some materials that we can deal with in civil engineering are listed here. We have, like we said before, higher values of fracture toughness for metals, pressure vessel steel 210 megapascal square root of meter, copper 110 and so on. So, metals have relatively higher fracture toughness values. And if you see here, the more brittle materials have much lower, almost 2 orders of magnitude lower. Glass, cement paste, concrete have very low fracture toughness values. So, they crack more easily and undergo brittle failure. Nylon for reference here would be intermediate, slightly higher than these brittle materials, but still not comparable to those of metals. Another way of considering fracture involves the energy release rate. Instead of the K1, which is the stress intensity factor, we can look at fracture mechanics in terms of the energy release rate. Whenever a new crack is formed, a surface is formed, and for this we require energy. So, all crack extension requires energy to be available for the crack growth to occur. This energy should be sufficient to overcome whatever resistance that comes from the material itself, and this material resistance can come from the new energy that is going to be created, plastic work or the work that goes into the yielding, and any other type of energy dissipation like heating, noise and so on. All that is some form of energy that accompanies a crack. We define what is called the energy release rate as the rate of change in potential energy with crack area. We find what is the rate of change of potential energy for every unit crack area to be created. This again for a linear elastic material. What Irwin found in 1956 was a fracture criterion could be given in this form, where G is the energy release rate. This now depends on the stresses, the load applied and the body, the shape of the structure, shape of the element and the defects. This has to be greater than or equal to a material parameter, the critical energy release rate or the fracture energy. So, this also could be a failure criteria, but these two failure criteria that we have seen, K1 greater than or equal to K1C and G greater than or equal to GC, are not independent. It was found that K1, which characterizes the stress and displacement fields near the crack tip, which is a local parameter, we are looking at what happens near the crack tip, and G, which quantifies the net change over the body, how the potential energy changes due to this crack extension, which can be described as a global behavior, are related, that K and G, K1 and G are related. In Irwin in 1957 showed that there is a unique relation between K1 and G. G is equal to K1 square over E prime. Okay. So, what we looked at previously are not two independent failure criterion, but they are related, and K1 is a parameter which is coming from the near tip stresses and displacements, and G gives us the global change in energy. E prime here is given as E for plane stress and E divided by 1 minus nu squared for plane strain, nu being the Poisson ratio. Fracture energy can also be determined, and this is a chart again from Ashby and Jones showing typical fracture energy values. We find again that the fracture energy for brittle materials like ceramics, rocks, cement, glass are at the bottom. We have here the group of brittle materials, and at the top we have the pure ductile metals and the alloys that follow. So, again we find that these materials fail in a brittle manner, these materials will not fail in a brittle manner and would rather yield. Polymers are somewhere in the middle. We have epoxies at the bottom and less brittle polymers at the top like polypropylene, and composites in the again in the middle. The units of fracture energy or the critical energy release rate are joules per square meter or Newton per meter. We had discussed brittle ductile transition, that can also be now related with the fracture toughness and fracture energy. We find, like you see in the graph on the left, that fracture energy increases with an increase in temperature. So, fracture energy increases with an increase in temperature. So, a ductile metal when it becomes colder will have a fracture energy that is decreasing and can become brittle and fail in a brittle make. Fracture energy also increases when there is a decrease in loading rate, that is, as the loading rate increases, a material will have lower fracture energy, it can become brittle. The fracture energy increases as the loading rate decreases. If you load slower, the fracture energy is higher, there is a less tendency for brittle failure when you load very slowly. When you load very fast, it is you see a decrease in fracture energy and a higher tendency for brittle failure to occur. A third case which shows an increase in fracture energy is a decrease in triaxiality. Triaxiality is the confinement and the degree of constraint. As you remove constraints, the fracture energy increases, opposed to when you have increasing triaxiality, the fracture energy decreases and you have brittle failure. This was like in the case of the bridge that we saw from Milwaukee, where there was higher triaxiality leading to brittle type of failure even though the material is characteristically ductile. So, this is something interesting that you should remember, what causes a brittle to ductile transition and how it can be related to the fracture energy. Whenever the fracture energy is lower, the tendency for brittle failure is higher. When the fracture energy is high, you can have more of yield type failure, ductile failure rather than brittle failure. Here you see how fracture toughness varies with temperature for a low alloy structural steel. In this curve you have on the y axis fracture toughness, x axis you have temperature, and you find that as temperature decreases, the fracture toughness decreases. The material is becoming less ductile and more brittle as the temperature is decreasing. This is the corresponding trend for the yield stress, which keeps decreasing as we increase the temperature. Yield stress increases as the temperature decreases, whereas the fracture toughness decreases as temperature decreases. The material becomes little bit stronger, but more brittle as the temperature drops, and this is what gave rise to the failures of steel elements in the ships that we saw in very low temperatures. In terms of loading rate, when the loading rate becomes faster, here we have on the x axis the loading rate and y axis we have the fracture toughness of steel. We find that as we load faster, the loading rate is higher, there the fracture toughness decreases. That is, there is a tendency for more brittle failure when the loading rate is faster, and the failure would be more ductile when you slowly load it. This is the reason that we intuitively always try to break things very fast when we want them to crack. we apply a very fast load when we want something to crack into two, where we are intuitively decreasing the fracture toughness by increasing the loading rate. So, we will stop here with this part. We have introduced linear elastic fracture mechanics, we have looked at the concepts, and very interestingly we have seen how at the tip of a crack we can have very high stresses, much higher than what is applied far away, and in the case of linear elastic fracture mechanics the stress can become singular or infinite at the crack tip. We then went on to define failure criteria in terms of the stress intensity factor K1 and the energy release rate G, and in both the cases fracture occurs when these parameters surpass or equal the corresponding material property. Fracture occurs when K1 is equal to or greater than K1C. K1C is now the fracture toughness, a material parameter, or alternatively we can see that fracture will occur or crack propagation will occur when G, the energy release rate, is greater than or equal to G sub C, which is the fracture toughness or the critical strain energy release rate. We also saw what happens to these fracture parameters under conditions of increasing temperature, triaxiality and loading rate, and we found that under these changing conditions there can be a ductile to brittle transition or brittle to ductile transition, and this could change the way the material fails. A ductile material could end up failing in a brittle manner and vice versa. In the second part of this lecture we will go on to see how different materials fail in fracture, what happens at the crack tip, what controls the crack resistance. We look at metals, we look at polymers, we look at concrete, and we look at some of the models which go beyond just linear elastic fracture mechanics. These could be called non-linear fracture models, and we will see some applications of these models. And in the end of the next lecture we will also bring in the effect of probability, the variations in the defects that we see in different materials, and how the probability of the defect occurring can change the strength that we get when you have a brittle failure. Thank you.